I'm supposed to talk on this 2D materials for device applications. It's a bit, it's a vast topic, so it's very difficult to really give some specific part of this two-dimensional material as device applications. Rather, what I'll do to kind of, I'm not supposed to talk here about my own research or something. So I'll give you an overview of, two-dimensional material, and definitely I'll be stressing on how we fabricate device. But before that, if some new researcher wants to start in his or her journey in two-dimensional world, then which way he or she should start, okay, or what are the opportunities, what are the challenges. I'll mostly kind of concentrate on those things, give you some insight, okay. Kind of I'll be touching all possible parts of two-dimensional material, starting from the synthesis. Finally, definitely my stress will be on device applications, okay, on this one basically device fabrication, because applications are, you will find thousands of different applications, not only from physicists, rather more from material scientists, material chemists, other engineers. So I will start by introducing a two-dimensional material. Most of you will find maybe a little bit kind of too low compared to your research, but just to make it a complete story, I will start by introducing two-dimensional material. Then I will go to various synthesis techniques of two-dimensional material, how we characterize them, okay, and then finally device fabrications and some glimpse of applications of this two-dimensional material. So what do we understand by 2D material? Okay, it's not that before graphene there is no 2D material. Okay, there was. People are studying 2D material, since long time, but maybe the nomenclature was not that popular at the time. Okay, so generally we understand by 2D material is that electronic motion or interaction should be confined in 2 dimension. That is the kind of one line, definition of what is 2D material. So before graphene, okay, there are a lot of 2D material like this, which nowadays we should call non-van der Waals, 2D material. It's a fancy name. Okay, it can be a bulk crystal. Okay, what happened is that these electrons, this layer of electrons, they are separated by some non-conducting material, or say this channel, if you consider this is as the horizontal channel and this is the vertical channel. So the vertical channel is very resistive. So electron prefer to move on this direction. So even if you make a connection here and here, you will be studying the properties of 2D material, definitely not from a single layer, but maybe a collection of those layers, and if the properties doesn't vary too much from layer to layer, you will be more or less seeing what you are supposed to see in a fancy 2-dimensional material by just taking one monolayer. Okay, and people were studying these materials or even 1-dimensional materials since long back. Okay, but anyway, these days we classified them to make ourselves kind of more, we feel that we are in a high position. So we call it a van der Waals 2-dimensional material, where these layers, they are isolated from each other. There is no bond, okay, between them, means not chemical bond. There is a van der Waals interaction, and the classic example is graphite. Okay, so you have this crystalline one, and if you are if you could discovered it long time back how to exfoliate it, okay, then that would have been great. But okay, once you know how to exfoliate it, you can get a monolayer of graphene, and this is possible in this van der Waals 2D material. And in non-van der Waals 2D material, it is very difficult to make a monolayer. Okay, these days people are coming with new ideas, new techniques to get 2-dimensional material out of this non-van der Waals 2D, monolayer out of this non-van der Waals 2D material. Okay, so it's not that research is only going on van der Waals material. Lot of research these days is going on this non-van der Waals 2D material. Okay, it's kind of renewed interest to find the monolayer of these materials. So what are the advantages of 2D material? Okay, this is the main important thing. Okay, it's actually after the discovery of carbon nanotube, a lot of people are very excited. They started working on quasi one dimensional system, made nanowire and all those things. But there is a problem with carbon nanotube in terms of application. The reason, the problem is making field effect transistor. Okay. So the gate length you cannot really reduce below a certain parameter because of the gate leakage, or it's basically in more like engineering term, it's short channel effect. There is also problem with the depletion layer. But in two dimensional material, people found that now you can solve almost all those problems using this van der Waals 2D material. So the best thing is that it has a layer dependent properties. So here you have a MOS2, which is again exfoliated. You have 1 layer, 2, 4, 6 bulk. Okay. And this is a theoretical calculation which shows that if you go from bulk to monolayer, you can see that the band gap shows a transition from indirect to direct. Here your direct band gap is much higher, and so there you have indirect band gap, which is preferred ones. Okay. But once you go to a monolayer limit, then you have this direct band gap, which is kind of the smallest band gap now. So these materials, this monolayer of MOS2 behaves as a direct band gap material. And what are the consequences? There's a huge amount of consequence. The huge consequence is this enhancement of PL. I think 10 to the 4 is the theoretical calculation. Practically, you see 1000 times enhancement, sometimes even less than that. But indeed, the monolayer MOS2 shows a huge enhancement in PL intensity. Okay. These days you are kind of familiar with all those things, but just to kind of make it a coherent story, I am going through all these things. And other advantages is this high mobility. This is something very important because all electronic applications, even or like future quantum technological applications, will rely on this mobility. Okay, whatever you are able to have access on this 5G or 4G, that is possible because of this high mobility. So if you don't consider graphene, let's take a look at room temperature. What is the mobility of your other material? Like silicon has 600. It's at the carrier concentration of 10 to the 12 per centimeter square. Gallium arsenic is slightly more than 4,000. This is close to 8,000. Indium arsenic 20. Indium bismuth it is 30, and graphene just as a flake is 25,000. This is not suspended or anything. Okay, not low temperature, just room temperature. This I think is little bit old. It's from this Taiwan Semiconductor, the famous company which makes your chip of iPhone and all those things. But this is exfoliated one. If you make your graphene by epitaxy, it comes around 3,000. CVD growns are even not that great, but not recently. I think last. I think this is a little bit old. I think even CVD grown one people got around 10,000. Okay, at least a Japanese company I know that they are kind of selling this CVD grown graphene over a large copper foil, which comes around close to 10,000. Okay, electron saturation velocity. This term, I think if you have read your field effect transistor geometry, what it says is that you keep applying you increase the voltage and how the velocity of electron will increase. It's not that it will keep increasing. After a certain time, it will interact more with the lattice and it will basically start dissipating. So above that, you cannot really increase the velocity. So your FET characteristics will go like this and then it becomes flat. Okay, that flatness comes from this saturation velocity. Okay, saturation velocity you can see is even also higher for graphene. Ballistic mean free path. Okay, that is definitely higher in case of graphene, but the main problem is the band gap. Graphene doesn't have a band gap, so you cannot really turn off your transistor. So you don't have an on off. So now you cannot really use it for digital electronics. So all your dream now shatter here. You have to look for analog applications. People are doing it. Okay, they are smart. Other advantages, and this is a great advantage is that there is no dangling bond. Being a van der Waals material, graphene, not only graphene, I mean all these MOS2 or layered materials, they don't have any dangling bonds, and that helps in various ways. One simple or kind of most important thing is that they have very less interfacial traps. Like if you take a silicon and try to thin it down and make a silicon transistor, then below a certain level what will happen, your surface dangling bonds, their contribution, I mean the contribution of the traps will be kind of more than your kind of whatever you are expecting from your channel. So, it is very difficult, you need to passivate, do a lot of stuff which is kind of tricky, but we should remember that silicon is still the champion guy. Okay, I mean there is no technology, I don't see next at least 15-20 years that is going to replace silicon completely. There will be compatible things, but silicon will still be there. Okay. So, yeah, there are a lot of other advantages. These materials are ultra strong. Graphene is probably the strongest material that you can think of. You can put them on any substrate. That is something very good, because this other high mobility material, gallium arsenic or indium bismuth, indium arsenide. Okay. These materials, they are not easy to grow. Generally, they are grown either using MB, molecular beam epitaxy, or MOSUVD, okay, metal organic chemical vapor deposition. But they need a proper substrate to grow these things. You cannot just grow it on any substrate, because you need to have the lattice matching so that the strain is less, okay, because that will decide how good or how high mobility you will be getting. But these 2D materials, you can exfoliate them using your Scotch tape and put it on anything you want, okay, almost anything. This is something also very important, very easy to make the heterostructures, okay. Again, you don't need MB. If you want to make p-n junction heterostructure, you just exfoliate p-type and put n-type material on top of them, and that's it, okay. You will get a nice p-n junction. Though the mechanism is completely different than your conventional p-n junction in semiconductor, because there you have a depletion layer. I will just touch briefly on that. And it is ideal for flexible device application, because it is combined with two things, that it is ultra thin and at the same time it is ultra strong. So, both these helps in making flexible device, because you can really apply huge strain, that something is amazing. So, lot of applications, especially your sensors which are body mounting and all those things, their 2D material is a really great promise. And ultra miniaturization, because you are already in the monolayer limit. So, less than 1 nanometer, I mean it is already highly miniaturized. Now, there are a lot of naturally occurring van der Waals materials there, okay. Whatever your MOS2 of either 2H or 3R phase, okay, or maybe tungsten disulfide is called tungstenite, okay. All these, even now the list of naturally occurring and lab made 2-dimensional material probably will go, combining them will go maybe more than 1000 or something, okay. But things are available naturally, though we really don't use them, okay. What we do, we try to synthesize them, okay. Either we or our collaborator, they synthesize them for us. So, how do we synthesize these 2D materials? Primarily, these three processes are done. One is exfoliation, that basically gave birth of this field, okay. Physical vapor deposition and chemical vapor deposition. There are a lot of other maybe techniques, not so popular, but these three are the most popular technique. So, first is the exfoliation. Now, exfoliation also has two major branches. One is the mechanical, or some people call it with a fancy name as the micro mechanical exfoliation, and is the second one is the chemical exfoliation. Exfoliation you can do either by applying a normal force or shear force or by fragmentation, and this is the first that people started using the Scotch tape, how to exfoliate graphene. There are advantages and disadvantages. Advantage is that you will get ultra clean monolayer, okay. It will be free from all sorts of chemicals or adsorbates, all those things. So, if you want to study some physics where the electron interactions or some other interactions are really important, then you have to, this is the way to go. You cannot really study that using a CVD grown graphene or some other material grown by any other means. So you have to go for exfoliation and mechanical exfoliation, not even chemical exfoliation. The problem is that you cannot get a large area coverage. You have to exfoliate and have faith on your luck and search under microscope where we will get some monolayer and then try to make device. Okay, try to use that. And also it's a very low yield. I mean, on a good day you might get couple of monolayer on the same chip, but on a bad day you might end up spending 50 chip without getting any monolayer. Okay. And this great technique of using Scotch tape gave Nobel Prize on 2010. Okay. Next exfoliation is chemical exfoliation. Actually, chemical exfoliation people were using long time back. Okay. Even if I remember correctly, when in 1970s people used chemical exfoliation to make this kind of two-dimensional material, but they really didn't realize that they are making two-dimensional material. But more important thing is that it was not that clean, or you will not get quantum Hall effect on that. Okay, that's the main thing. So, chemical exfoliation can be done either in a liquid phase where you use some solvent to intercalate and then sonicate. Generally use stick sonicator for this. Okay, and you will get this kind of thin sheets dispersed on your liquid. Okay, then you can even use it as ink. I mean, these are available these days even commercially. Okay, some conducting ink. Even recently people found superconductivity in, I think, NBAC2 ink. So, this is also kind of gaining some maturity. Or you can also use intercalation, okay, where you intercalate lithium, and then lithium is just one example. You can intercalate with the lithium and then say react with water, and again you can get this kind of dispersed nanosheet. The great advantage is that it's very good for large area applications. Okay, you'll get that ink and you can paint it. Okay, but the problem is that it's not very controlled. Okay, in that ink you will get mixture of all sorts of things, monolayer, bilayer, few layer. That is the problem. But I mean, it already got a lot of applications, especially this LED sensors. Okay. So, next way after exfoliation is the physical vapor deposition. The great advantage is that it's a pretty simple process, okay, and you can place your substrate at kind of room temperature, even you can cool it, okay. So, substrate temperature can be pretty low. You can use any kind of substrate, even that is a kind of heat sensitive, temperature sensitive substrate. You can also use, flexible substrate to coat this thing. It's very easy to coat them over a large area, okay. But the problem is that it's very difficult to grow monolayer. Okay, if you are happy with few layer, then it's okay. People are trying to grow monolayer, but they are not very kind of reproducible. Okay. Also, this maintaining stoichiometry is sometimes very difficult. You may be depositing MOS2. You are thinking that I grew MOS2, but it may be MOSX. Some X is not 2, close to 2, maybe plus minus something. Now, how you depending on the way you are heating your precursor, it can be either, if it is resistive heating, then you call it thermal evaporator. If it is through electron beam, okay, it's E-beam evaporator. If you are using a laser, then it's a pulse laser deposition, but all are physical vapor deposition. Okay. There is another way to make this vapor flux, that is by ion or plasma bombardment. All of you are familiar with sputtering, okay, or you can use also IBD, ion beam deposition. Okay. So, this what is sputtering? Sputtering is a machine where you make a plasma, mostly argon plasma, and then you guide it to a material, okay, which you want to deposit. So, that plasma, high energetic plasma or the ions will come and hit that material, and physically it will remove that material. So, basically if you are kind of close to a mud puddle and throw some stone on it, you splash some mud. So, it works almost in the same way. Okay. So, the next thing is chemical vapor deposition. This is one of the most popular technique for growing monolayer this two dimensional material. Those who do not like to kind of do exfoliation, or those whose application really does not require that clean sample. It is a highly scalable process, is commercial process. Okay, all your this SiO2 wafers are basically grown using CVD. I mean the SiO2 part. You can get really large area coverage monolayer. Here now you can get monolayer. Okay, without any without much problem. You can get pretty clean sample. Okay, but the problem is this one. It needs optimization of various parameters. Some of them and some of them it's very difficult to identify. Sometimes it may be the time of the year, it may be rainy season, you may not get the monolayer with the same parameter because the humidity of your environment has increased. Okay, so there are a lot of known and difficult to know parameter. I mean difficult to identified parameters are there. But once you optimize it, generally it works. Okay, at least for graphene and other thing, people have optimized it quite well. Okay, but the problem is that generally the substrate temperature is high. What I have seen here is a called hot wall chemical vapor deposition, which is the most common thing that we use in our lab. We have a furnace, we have a quartz tube inside. So you are heating that quartz tube. That's why it is called hot wall. There is also cold wall chemical vapor deposition, where the heater is not outside. It's basically wherever your precursors are, heater will just sit over there. So your wall remains cold. Okay, that is called cold wall chemical vapor deposition. Now chemical vapor deposition, again depending on the conditions, it can be atmospheric CVD, means it works at atmospheric pressure, you do not need vacuum or something, or you can convert it into a low pressure chemical vapor deposition for certain material. That is also very helpful. You get cleaner, or sometimes it is easy to get continuous monolayer sample using low pressure chemical vapor deposition. Okay. Or there is other sophisticated part like plasma enhanced chemical vapor deposition, especially for depositing oxide, SiNX mainly, silicon nitride. People use plasma enhanced chemical vapor deposition. Even for some SiO2 also, like insulating material, people use this PECVD. Okay. Now by any of this technique you grow your sample, okay, either by exfoliation or by CVD or by PVD. Okay, you got something on your chip. Now you need to find out what is the thickness of that 2D material. You cannot just say that okay, I got a, I mean I do not want to characterize it and I got a monolayer. Okay, you have to characterize it. So what are the things that you do? Most popular technique is Raman spectroscopy. I think it is popular because of the graphene again. Okay, but nowadays we use it for almost everything. So anyway, you know that there is Stokes anti-Stokes line. Okay, direct transition is called the Rayleigh transition. You put a filter to cut the Rayleigh. Okay, and depending on how fine your filter is, you can go to the lower wavelength of your Raman shift. So again, Raman spectroscopy uses two different things. Okay, to identify the thickness of the two-dimensional material. One is the peak position or the intensity ratio. Okay, if it is TMDs, okay, like MOS2 or something, then what you need is the peak position, okay, the spacing of the peak to identify whether it is monolayer or not, okay, monolayer or bilayer, or it may be bulk. So like in case of MOS2, you can see that if you go from one layer to bulk, this peak position they are changing. We really do not care about the intensity, what is the relative intensity in this case, okay. But if you go to graphene, the peak position does not change. What changes is the intensity. And just by looking at the intensity, you can tell whether it is a monolayer, bilayer, trilayer, four layer. I mean, it is very accurate. It is amazingly accurate. Even this trilayer, if you look carefully at this peak, which unfortunately I cannot zoom here, then looking at the pattern, you can tell what is the stacking of the trilayer. It is so accurate. It is damn accurate. Okay, just looking at the peak, I mean whether it is rising like this or it has rising like this, just looking at you can tell that whether it is what kind of stacking is there in the trilayer. Okay, so this is one of the most common and popular technique, because not only the thickness that you can determine using Raman, you can also identify if there is an effect of strain whether what is the type of doping, okay, if you have defects, more defect or less defect, or what kind of defects are there, interlayer coupling, band structure. So, you can see that Raman spectroscopy, I mean, why it is so popular these days, especially the 2D community. Next is the photoluminescence spectroscopy. Okay. This also you can use, but it is not useful for all the monolayer material, all the 2D material, but especially the TMDs, it is a very useful one, where you generally see a transition from direct to indirect to direct band gap in the monolayer limit, because the PL enhances like anything. Here you can see that a monolayer and bilayer WS2, the PL is is largely different. So, here it is again example of MOS2. You can see that from one layer to bulk how the PL is changing, it changes drastically. So, just as an example, okay, that the monolayer MOS2, it absorbs almost 10% of the incident light, okay, energy should be above the band gap. Now, if you compare with the bulk crystal, it is almost 1000-fold increase, and that is the kind of reason that you see this high photoluminescence in this material. And just compare with a silicon, how much light you absorb. Okay. So, the reason that you cannot make ultra thin silicon solar cell is that silicon has an indirect band gap, so it is not very efficient. Normal silicon actually, I think on an average it absorbs only 35% or something, even the thick silicon, whereas a monolayer MOS2, which is a 0.7 nanometer thickness, can absorb 10% of the incident light, which is amazing. The next technique you can use to identify the thickness is atomic force microscopy. This is again, I mean, if you have the machine, then you can use it and find the thickness of monolayer. If it is graphene, it is 0.4 nanometer, MOS2 is around 0.65 nanometer. Okay, I mean, this is, these days how AFM works. But not everyone has the access of this thing, and it is not always easy. You might have a long queue to figure out, at least do one of these, use one of these instruments to figure out whether you got a monolayer or not, but you want it all the time. Okay, probably one day you are making 50 devices, and you cannot do 50 times AFM or Raman to figure out whether I have a monolayer or not. So, this is a great discovery, that I should say, where people figure out that on a certain substrate you can see monolayer. Okay. And in this paper they have shown for various types of substrate what is the thickness of that SiO2 or the insulating material required. Like here it is SiO2, here it is aluminum oxide, it is hafnium oxide, PMMA or PVA, and again it is a aluminum oxide on top of aluminum. These are all on silicon, this is on aluminum. So, you can see that to see one layer graphene you need this kind of thickness, and then if the monolayer is there you will be able to see it. So, you do not need any sophisticated instrument, just a ordinary microscope will tell you whether you got a monolayer or not. I mean, you have to train your eyes a little bit, but I mean it is highly doable. So, here is a kind of list of the most commonly used material and what is the thickness that you should be using. And what we do in our lab, okay, we mostly use SiO2 on top of silicon coated substrate. The thickness is around 280 to 300 nanometer, which gives us kind of the sweet spot. I mean, if you have noticed that there is another sweet spot that is close to 80 to 90 nanometer of SiO2. The reason that device people do not use that is that SiO2 is highly prone to pinhole, so it can leak. So, we generally require little bit thicker SiO2. If you are doing optical studies, then 80, 90 nanometer is perfectly fine, you can use that. Okay. So, this is just some example of MOS2, WS2 and WAC2 on monolayer on this substrate. Just to show you that, okay, what are the various types of 2D material people are working these days. Whatever you can think of, it is listed here. I mean, this list is very short. There are almost now probably thousands of 2-dimensional material with all sorts of properties. So, you get metallic, insulating, superconducting, charge density material, whatever you can think, almost everything is there these days. This is a big advantage of 2-dimensional material, especially the van der Waals material. That is, you can stack them like a Lego block. You can stack them on top of another. If you want to make a PN junction, you just put one p-type material and n-type. If you want to make some insulator, semiconductor, superconductor junction, you can just stack them. Okay. So, this is a big advantage for this. Now, how people do this thing? Okay. This is kind of a, people call it transfer stage. Okay. You put under a microscope with a long working distance objective, and you use some PDMS or other material to exfoliate your monolayer, okay, and then align them and press it, and after this you should come here. If you release it slowly, generally the property of PDMS is that it is a viscoelastic material. So, if you release it slowly, then it will release the monolayer. If you do it fast, then it will not release. Rather, if you want to pick it up, then you have to do it fast. Okay. But the same material, if you just now release it slowly, it will leave that material. It is kind of this corn starch solution. It is kind of, if you hit it hard, then it is solid. If you push it slowly, then it is liquid. It is kind of like that. Okay. So, this is kind of a well known and well established technique. Everyone has this thing these days. We also have one. Tamagna made it. Okay. So, we have heater and whatever the required kind of a jugaad thing. Even the microscope is jugaad. Okay. So, what are the advantages of van der Waals heterostructure? Here I am not considering all sorts of heterostructure, just taking the PN junction just to compare. So, the conventional PN junction, you have regions which is depleted. Okay. It is coming from both sides, and that you have this uncompensated dopant ion which makes you this built-in potential. Okay. That is your depletion layer, and that puts some restriction in terms of when you are miniaturizing your device. You cannot really make something below the depletion layer, and depletion layer is generally of the order of 100 nanometer, okay, or even sometimes more. That was one big reason that you cannot make a PN junction radially on a nano wire, which people tried because the entire wire will be depleted. Okay, you cannot really make a PN junction. But in this case, you can take a monolayer, p-type, n-type monolayer, put them, you will get a PN junction thanks to van der Waals interaction. There is no transfer of charge. Okay. In this case, you will have the carrier transport via diffusion or drift process, but in this case it is tunneling because you have that van der Waals gap. Okay. So, this is it is a completely different charge transport mechanism in this kind of PN junction. And the great thing is that, okay, it is atomically sharp, definitely. Okay. There is no dangling bond. Okay. It is highly gate tunable. The interfaces get tunable because if you are having this P and N type material, you can apply gate and you can change their carrier concentration. Okay. So, that gives you some extra degrees of freedom, where here in case of the PN junction, it will depend on the dopant type and their concentration. Okay. If one side is heavily doped, then that thickness of the depletion layer will be less. Other side, if it is lightly doped, it will be large, just because you need to compensate them. Okay. So, fine, you got good material, you are lucky to stack them or made maybe twisted structure. Okay. Up to that you are fine. How to use them? Okay. Now, I am going to kind of talking about device, and my definition of device is something where you need to make a connection with your 3-dimensional world. We cannot really go to the 2-dimensional world and kind of touch them and use them. We cannot put a meter on that. Okay, we cannot send current. If you are doing optical property study, your life is bit simple if you do not have to apply any voltage or anything. Okay, but I do not call them device. Whatever device I will be calling, okay, today is where the 3-dimensional world like us can talk or can communicate with the 2-dimensional world or the 2-dimensional material. So, you have to make connection to either these individual layers, okay, or you can make a gate or whatever is that. So, how will you make the connection? Like here, this is a monolayer MOS2. Okay. We have to make this source and drain and a gate. It can be a back gate or top gate. Here it is a top gate. Okay. Or you can make even both. Okay. So, how to make this connection? So, whatever device I will be calling is basically making electrical connections. And what are the various types of device you can think? You can think of almost anything. Like in this case, You have MOS to WAC2, so that's basically a PN junction type material. So you make connections to that. Okay. It can be even a light emitting tunnel transistor. You have to make connection to that. It can be a single defect light emitting diode. You need to make electrical connection. Okay. It can be a electroluminescence or photocurrent generation from again this kind of material. You need to make this connection, or it can be a photo detector based on graphene, which is kind of the highest during that time, 50 gigabyte per second. You need to make contact, and making contact is the main issue. So people knew about nano structured material since long time, okay, ancient time. The reason that electrical properties were not explored earlier is just because people didn't know how to make the connection. So once with the advancement of lithography, now we are having this leverage that okay, we can make a device easily. So how do we make device? Okay, everyone knows photolithography. It has 3 major steps: coat, expose, develop. Done. Okay, life is so simple. So you coat the photoresist using a spin coater, all you know. Then you have a photo mask. Probably here at IISER you don't use that. You use a laser writer. That's a vector writing. But in a conventional lab, you will get a photo mask, and then you expose with a light. Then you develop with the developer, and you will get this pattern, and then you deposit whatever material you want. Do the lift off. You will get your device. So just to kind of as I'm starting from very scratch, so I will tell you all this. Probably all of you know about it. So the resist, it's just an organic component. So in your lab you use generally S1813 or S1814. This 1314 is basically the concentration. It tells you after spin coating on a particular RPM what thickness you will be getting. There are reasons for it. If you want to make something that is fine feature, then you cannot take very thick resist, you have to take the thinner one. So if you want to take thinner one, you just go down the number, this S number. Okay. So use S1815, S1805, that is the thinner one. If you want to make something thicker, then you use S18, say 24 or something, that is the thicker concentrated one, which will give you a very thick resist. Okay. So generally we use 2 types of resist. One is positive, another is negative. What is positive? Positive photoresist is this: the part that is exposed after developing, that will get removed. So if you deposit metal, it will be deposited here, it will remain here. Okay. Or if you want to do say etching or reactive ion etching or something, it will etch this part. So that is called the positive photoresist. So S1813 or S related resist or positive photoresist. IISER resist are generally a negative photoresist. So you will find lots of different resist. So negative photoresist, whatever part you will be exposing, that will get hardened and that will stay, rest of the part will go. Okay. Especially it is very useful for you want to etch, say you got a monolayer graphene, okay, on a very small area, and you want to etch rest of the thing. So you want the resist to stay there to protect the monolayer part, and you want everything to get washed, clean. So if you do RIE, you have to use this negative photoresist. You just protect that part, because if you want to use positive photoresist, then you have to expose the entire chip, which is very difficult. Okay. But in this case, you just expose that small part, it will get hardened, and then you wash it and do RIE to clean unwanted portion from it. UV light source generally use sodium, no, it's not mercury vapor lamp that people use. These are all lab based thing. I will come to the commercial thing just to show you kind of some fun facts. So you probably heard about these things, okay. G line, H line, I line lithography. All they are talking about what is the wavelength that you choose to do the lithography. Okay. Sometimes if your machine is not that sophisticated, it just expose whatever the UV light is there, because probably the photoresist that you are using really doesn't care about that much, and your limitation of feature size is maybe around 2 micron. Generally you cannot go below that, okay, using the lab based technique. And photo mask, mostly you use a glass plate which is coated with chromium. Okay. So whatever the pattern here, that the feature size you will get transferred 1:1, okay, kind of ratio. So, generally what you get is around 2 micron feature size with a hard contact. There are some small terminologies are there. If you are using say I-line lithography, okay, 365 nanometer, then it is better to use quartz because glass is not very transparent in the UV region, but most of the cases just normal glass plate with chromium is fine. These things were crazy costly, unfortunately, okay, because people will be making one for you. Okay, you need a particular pattern for your sample, so it's a bit costly. This is a typical mask aligner. I think the picture is this Carl Suss MJ6 model, if I am right, that you generally use in the lab. Okay, unfortunately, we still don't have. So this is the UV part. Okay, this is the mask holder, and here you load your sample. This is a small cassette kind of thing where you load your sample. This basically applies nitrogen pressure to do the hard contact, because to transfer the pattern nicely you do not want a gap between them. So, you apply pressure using the air, okay, and when there is a particular type particular value of pressure you should be applying. So, it is kind of called hard contact, and that will give you the best result. So, if you want to get something like a resolution of 2 micron, you have to do it in the hard contact mode, but some kids who are not very aware about the system, they can break the mask, and mask is very costly. So, mostly people go with the soft contact. Okay. But your life is not that simple that you just have a optical lithography and you are done. You need E-beam lithography also. The reason I will tell you quickly. So, again E-beam is I will not go very deep on that. Again, there is a positive photoresist, negative photoresist. PMMA that you use in your lab is a positive photoresist. What you do not use is HSQ, that is a negative photoresist. The advantage of HSQ is that you can make very ultra thin thickness insulating layer or something. So, if you are making a top gate, HSQ is something great, but that is a negative photoresist. Okay. In conventional lab, like everyone has ACM, so what they do, they just install this blanking electrode, beam blanking electrode they buy from Wraith, okay, that is much cheaper than anything else, and you can convert your conventional ACM into a E-beam writer. Okay. That actually is a great thing, especially for doing research at low budget is great, but this is not the machine, because you can see that the accelerating voltage is 100 kV. This is a schematic of a dedicated E-beam lithography machine, which cost I think these days around $6 million. Okay. In India we do not have any. Okay. But anyway, if you put this number as 30 kV, then everyone has it in the lab, okay, and we have a beam blanker, and the beam blanker will tell you how to write the pattern. So, how it writes the pattern? You basically just consider the scan mode, forget about the vector mode, generally we do not use vector mode. So, in the scan mode your beam is scanning here. So, up to this region the beam remains blank, okay, it does not fall on the substrate, only this region it opens, okay, and the beam falls on the substrate and then it closes, okay, it just scans like that, and you get finally this kind of pattern. What is the time? I do not have
15 minutes more.
15 minutes more, okay, I have to go really fast. I think fine. Okay. So, this is something a little bit technical, but I would like to show you, because when I came across this thing first, I was kind of little bit surprised. I know those who are doing E-beam lithography, you probably notice that if you are doing lithography at a low kV, then you need lower dose, okay, and at higher kV you need higher dose, which sound very contradictory to me. I thought, okay, at higher kV, at 30 kV I need a lower, I need a higher dose, and at 5 kV I need a lower dose, okay. The reason is the interaction volume in the bulk. So, to understand it very naively, it is kind of throwing a stone on a glass window, it will break, it will shatter, it will propagate everywhere. So, here also if you have a low kV, then the interaction volume is kind of, it remains here and it spreads everywhere, okay. But if you are shooting a bullet, okay, it will just make a small hole in the glass, so it is kind of like that, okay. You are shooting at a very high kV, the interaction volume is very less on the surface, at the deep inside it will expand, but we generally coat a very thin layer of resist. So, we do not see this part, all we get is only this neck part, okay. So, at 5 kV your interaction area is larger, that is why if you want to write say 200 nanometer pattern at lower kV, you use a lower dose because the spread is much higher there. But at higher kV, you have to use a higher dose, okay, and you will get finer pattern, finer feature. So, in case if you get stuck on something, you cannot make finer feature, the first thing should come into your mind that I have to do it at the highest kV available, okay. So, these days e-beam lithography, the resolution can go up to 5 nanometer with the 100 kV machine, not this SEM based one, the dedicated e-beam lithography is a bit long column, okay. But what we do in the lab, if you have only e-beam lithography or only optical lithography, you are not in a very good set, okay, you need both, because this part you make using photolithography, okay, which you can see that there is a 7 millimeter by 7 millimeter. If you want to write using e-beam lithography, it will take probably months to just make one pattern, but in photolithography it will take less than 10 seconds, okay, to at least to transfer the pattern. So, and then this intermediate, the finer feature that you make using e-beam lithography, okay. So, you need a combination of both optical and e-beam lithography to run your lab successfully, to make a device. Now, how to connect the encapsulated 2D material, okay, because if you want to keep it clean, suppose graphene we have covered it with a HBN, what to do? That is not very easy, you cannot just make pattern from top and make the connection. So, that idea actually came from a problem in photolithography. The problem is that like here, you know, it is a tellurine, okay, and Rohan made this nice device. You expect something like this all the time, but you end up getting something like this, okay. So, whatever you are seeing here, these thin layers are basically is a problem in the photolithography that is called sidewall deposition, okay. I will explain it very clearly. So, if you expose these regions, these are the exposed part, what you expect is after developing you will get something like this. This is the photoresist part, okay, vertical, but you do not get that. If you are using S1813, you get a 68 degree side angle, that is you cannot make it 67 degree or 69 degree, it will come 68 degree, it is the property of that photoresist. So, you have this side angle, okay, it is not vertical. So, when you deposit metal, okay, it will deposit like this much portion will be deposited on the side wall, okay. It will be definitely thinner than this part, okay. That is why you see that this is bit thinner. If you look at carefully, these parts are thinner than this middle part, okay. So, it is a problem in photolithography, but smart people have used it in 2013. Corey Deans and James Holmes group from Columbia and then published a science paper using this problem, okay. They figure out how to use this problem and convert it into a great connection technique that is called one dimensional connection, the edge contact. So, you have this material encapsulated, you make the photolithography pattern, you have the 68 degree angle, now you etch it, okay. Once you etch it, you will get this kind of structure. So, now if you deposit metal, it is going to connect your one dimensional, two dimensional material which is embedded under this two dimensional encapsulation, other like HBN or something, and this is known as edge contact. Today's all the great devices like which is showing great performance, all are made by edge contact, and it is a very successful one, okay. So, lab based is done. Now, here is the machine, you should all say thanks to this ASML lithography unit. All your mobile, iPhone, laptop is made by this machine alone, monopoly. There is no other machine in the market. Nikon and others were there, but they all went out of business. Why? Because of this guy. There is a, this is a stepper. I will just tell you quickly what is it. This is the cassette loading, the wafer loading part. This is the stepper. It can, align your sample, move your sample with the precision of quarter to millimeters, nanometers. Okay. You have the optics column. There is some vacuum chamber, and this is the extreme UV generation that ASML has discovered. It can generate 13.5 nanometer wavelength. Just the light generation itself is kind of a beauty. They use a two carbon dioxide laser. They fire tin on it. Then one laser finds the position. where it is kind of perfect, and then the another laser shoots, and there is a plasma generation happens of tin, and then electronic recombination gives you 13.5 nanometer light. So, I will just play you this video, hopefully it is going to work. Okay, so now it is finding the position. Once it found the position, then it shoots the actual high power laser, and that makes the extreme UV light. And because of that, you get your till now I think you get already 3 nanometer node. ASML said that by 2025 they will come with 2 nanometer node. Okay, so your mobile and iPhone or like laptop will be even faster. The only downside is that this machine cost is crazy. Today in Indian rupees it's 1,300 crore, and our budget for 2023 semiconductor is 3,000 crore. So, you can buy 2 of this machine and done. Okay, good. But so far so good. Okay, good, fine. Now, if your material does not withstand the lithography process, generally optical lithography process, because there is water that is used, a lot. I mean, semiconductor industry probably one of the largest consumer of water. So, the traditional photolithography needs water, but suppose you have a material, okay, which can easily dissolve in water. Here I have shown a CSPB BR3, again 2-dimensional material, okay, that we grew in our lab, but you can see that within 1 second it dies, it just get dissolves in water. So, what to do with this kind of material if you want to make a device? So, what generally people used to do is the drop casting, means you already patterned the electrode and then you drop cast. Okay, fine, it is a kind of simple technique, but there is a problem with this drop casting. The reason is that it may be a random orientation, there might be some debris between these contacts, so you will not get a good contact, and also the contact area will be very less. Okay, if it is uneven, you will not get a good contact. So, we will always prefer to deposit some material from top, okay, which will give you a better connection. And it will have a better contact as well. So, what we did, people are using some other techniques as well. We discovered a technique that is called sacrificial layer based technique. So, we have a CSPBR3 crystal, and here we use polystyrene as a sacrificial material. You can use any material, just you have to make sure that when you develop this material, it should not dissolve this water soluble thing. Okay. In this case, we can dissolve polystyrene in toluene, and toluene does not attack this one. So, what we do, we deposit polystyrene, and then we deposit photoresist on top of it and do the conventional lithography. We develop it in the water based, because polystyrene is protecting the sample. Okay. Once that is done, then we dissolve the sacrificial layer. Here it is toluene, so no water is there. Okay. We get the pattern, and then we deposit metal, and finally we do the lift off, we get the device. Okay. We are successful in making devices. We can, so like each and every step, you can see the PL remains intact. Here we deposited the gold pads, so the PL is not there. You can see that they are showing decent electrical properties. We even checked with various other materials, like in this case, we have tested with this is gold and this is aluminum, so it shows a diodic behavior. Okay. Here I think this is with indium tin oxide, transparent conductor. We made the connection using that. But there is a report in 2020 where it claimed that this vapor deposition damages this crystal, but we found that it does not damage. So, what we did, we deposited metal everywhere, and then we sonicated to remove metal from this one, and you can see that the PL is intact. Okay. So, it really does not damage. We also did AFM, we found that there is no difference between the roughness in this side and that side. In this case also, what we did, after deposition, we sonicate and removed one electrode, and the PL is still intact. In this case, we made transparent conductor, so even when the electrodes are there, you can see that the PL is intact, so it is not damaging. Okay. So, it is a kind of sacrificial layer is successful. But 2D, there is a problem of contact material. You cannot use any material, and that will not give you good contact. So, Saptarshi, his entire PhD was just to find a good contact material. Okay. He worked with Appelnzer in Purdue. Okay. So, you know Saptarshi very well. So they optimize like what are the materials that will give you the best contact, and I mean he has really some nice work on that and review. I think this is one of his review. Okay. Now what are the various possible devices? All sorts of devices that you can think. Okay, here like non-charge based and charge based. It can be a magnetic tunnel junction, spin logic, Valley valve, okay, quantum dot based one, resistor tunnel diode, it can be a tunnel field effect transistor, it can be a floating gate field effect transistor. These are just few of them. Okay. Let us take one example, photodetector. There are all sorts of photodetector. It can be a 2D heterojunction using a black phosphorus and I think it is indium selenide, or it can be from the same material. Here it is basically 2 layer and 1 layer, and that makes a heterojunction. Okay, I mean it's a homojunction, but that also works as a photodetector, or you can use a waveguide, blah blah blah, all sorts of things. Okay, so just on photodetector there are hundreds of different architecture which you can use, or you can stack them either 2D 2D, or you can combine them with 0D, 1D, 3-dimensional material. You can make heterostructure. So you have a countless opportunities to make devices, but there is a new twist after 2019, Pablo Herrera's work, that is you just take the same material and twist it at an angle, especially for graphene you get a flat band, and all sorts of interesting things are coming. Here just a review of, I mean it's a review on Nature Physics, where they showed that now you can have a quantum simulator with a condensed matter system. Okay. Earlier we probably heard only about this optics guys, mainly basically the laser guys, okay, where they can kind of do the quantum simulation, but now here condensed matter guys can also do all sorts of things, like you can make a triangular lattice, okay, you can have a correlated insulator, it can be a spin density wave, okay, you can have a spin liquid structure. So this is a triangular lattice, this is a, I think it's a just square lattice, this hexagonal one, and you can have even a 1-dimensional lattice where you can say Luttinger liquid behavior and other things. So just by using a twisted structure, you now again it's kind of exponentially increased the possibilities. Last bit, I don't know how many have heard about 2.5 dimension. This is again another nomenclature. Okay, what they do, they intercalate some other material between a 2-dimensional material, and this they call as 2.5 dimensional material, and some people are at least interested in this thing. They got some interesting result. Okay, thank you. Yeah.
It's information.
Graphene is not brittle. Graphene is damn strong.
So basically, like we use carbon fiber like epoxy, just industry that. We see it with graphene.
People are already doing it. Especially with graphene, not too much with graphene, but graphene oxide and other material they are doing. So they just make this ink. Okay. There is also this fluorinated graphene and other sorts of graphene people are using. So they functionalize them and then they use it. No, unfortunately not. I would like to see that. All your machine, I mean, chip is kind of made by that. Like whatever is below, kind of. These days they are mostly making 7 nanometer, 5 nanometer, 3 nanometer also, but 2025 they will be coming with 2 nanometer. And it's a photolithography. I mean, if you consider that 13.5 nanometer is, yeah, it's close to X-ray now, the extreme EV, right? I mean, that's why all others out of business. You don't hear anyone else. So it's a monopoly. Research gave them the monopoly. I mean, everything is robotic. There is no human involved. Okay. I mean, yes. Yes. So this is the machine that put everyone out of business.
Any other questions?
So 2.5D material, what they do, it's basically came from the intercalation. Okay, so you intercalate certain material, even like in graphene, you take bilayer graphene and if you intercalate lithium, then people observe superconductivity in those materials. But that is not the only one example. A lot of other material, what they do, even in TMDs, they try to put some molecule in between. Okay, and those molecules they apply stress. Okay, they try to expand little bit, expand it, and that changes the property. That gives them some new properties. Okay, which are not really available even if you make a just put one layer on top of another. So I mean, it's not a very common thing, but people have started working on that, and people trying to explore that as well. Okay, and why they call this 0.5 dimension is basically they're using this gap between these two layers. So it's a two-dimensional, and that the gap they call is the half dimension. So that's a 2.5 dimension material.
What about the presence of 2.5D magnets?
I am not aware of it. I don't know. Okay. Magnetism is not my part. You're asked me.
In 2D materials, the trap states or the defects are at the edges because that's where the growth stops. So we are making contacts right at the edges. So we think what we measure is like lesser than what actually is because of the trap state.
Yes, age is a big problem. Okay. Sometimes it can be advantageous. Like if you take MOT2, I think the age are kind of topologically protected, so they show some different behavior. Now, what happens, what I believe is that as long as it's a graphene, okay, it really doesn't matter. Okay. Because say there is no band gap, so it makes a pretty good contact, okay, while you are doing edge contact. But yes, if it is other material like MOS2 or other material, then it will definitely, at least the Fermi level pinning and other thing will become. Now, but people are smart, okay. They are trying different kind of contact mechanism to reduce this, pinning. Also, they are looking for right material to make the contact. I think recently they figured out that bismuth makes very good contact with a lot of these TMDs. The main problem is that if your contact resistance doesn't come below a certain level, then you will never achieve this desired on-off ratio in your FET. Okay. So your contact resistance has to be below certain number. I forgot that industrial standard number, but there is a number. Okay. And people are actually trying for it. Interestingly, in two-dimensional system, what people found that even just van der Waals contact can be great. Okay, it will be tunneling mediated. Okay, but that can reduce the resistance significantly. In MOS2, some people are doing, so contact engineering itself is one branch of two-dimensional. So some people are trying that only in the contact region, like if you're taking MOS2, which is a semiconducting material, then only in the contact region, they do some argon plasma treatment, which will convert it into metallic phase, and now you deposit contact material. Okay, that will make a nice contact because that part is now metallic. Okay. So that's how you can reduce the contact resistance. So yeah, I mean, people are trying to solve those problems.
Any further